All right. So for the actual analysis of the challenge data with EFTP plus B, our standard data vector for retrospace mocks consisted of five statistic. Well, we use three multiples of the galaxy power spectrum: monopole, quadrupole, and hexadecapole. Plus, we use this kth as a new statistic. It's a real space proxy. So basically, at some point, um, if you just work in richer space and use multiples, at some point you get sensitive to fingers of God that limit the application of perturbative technique, but then you can construct a proxy for the real space power spectrum and extract a little bit information at higher case that like typically is spoiled by fingers of God. So you can cancel fingers of God with this kth. So you can think of this as an extension of the power spectrum. And then we add the bispectrum monopole B0. For the covariance, we use the Gauss analytic covariance, which is fine on large scales. For the data estimator, we use the window-free approach developed by Oliver Hilcox for light cones and the usual Scacchiumara estimator for periodic boxes. So for us, it's also a test of the estimator of the different statistics. So this is another dimension in this challenge. And for the model, we use one loop EFT for the power spectrum and kth, and the tree-level bispectrum. We also tried one loop bispectrum, but then it was not very useful because it depends on around 40 nuisance parameters. So at some point, just all the information is dumped into them. Right, so this is our baseline data vector. Maybe if you could go to the next slide. Yeah, we performed several validation tests and also some additional tests. The most important validation test that I described before was the parameter drift as a function of Kmax. So for each mock, for light cone, for retro space, for real space mocks, we produce this parameter drift plots, and this is how we determine Kmax. Then we also checked that for given Kmax, our chi-square is reasonable, and when we fix some let's say baseline Kmax, baseline choices, we also did additional approach. We also did some additional tests on top of that. So we tested if the results are stable with respect to the data vector cuts. So at some point we would just remove the bispectrum, or would use only large scales of the bispectrum or the small scales, and so on and so forth. And if the results are stable, then we'll trust them. We also did some tests on syncretic data to check for the marginalization effects. We varied the covariance for the bispectrum. It's a little bit of a technical point because for the bispectrum covariance, you need the full theory model, so it will change as you change the best fit cosmology. So we also tested that. And the final test that we did, which is kind of interesting, was that we, for some of the mocks, okay, I hope this will not be a big thing to say, that some of the omega matter are very different from our fiducial omega matter, which is kind of similar to Planck. So some of the cosmology are really different from Planck. And the third omega matter was very different from the one that we assumed for the Al-Kapachisky test. But then we rerun the whole pipeline, including the estimator, to calculate the power spectrum for the new cosmology. And then we found that basically it doesn't have any impact on our results. So this is interesting to know that the standard Al-Kapachisky way of doing things, of estimating power spectrum, is very stable.
Hello, my name is Marcos Pellejero, and I am the team coordinator of the BACCO analysis, composed by Raúl Angulo, Mateo Cenaro, and myself. In this work, we used the power spectrum for real space and the power spectrum multipoles for Recife space to extract information about the cosmological parameters from the Beyond 2-point challenge. I know it sounds strange to use only 2-point statistics in a challenge named Beyond 2-point statistic. However, our methodology is able to push the study of the power spectrum to small nonlinear scales, unexplored by perturbation theory-based approaches. These scales are affected by nonlinear evolution, making them non-Gaussian. Higher order statistics also appear due to the non-Gaussian nature of structure formation, making these two concepts heavily intertwined. I am not claiming here that higher order statistics won't have extra information, just that part of that information can already be found in the nonlinear scales of the power spectrum multipoles. Let me very quickly explain the model we use in a nutshell. The model is based on a combination between matter-only n-body simulations for the structure formation and analytic approaches based on bias models to populate the simulation with galaxies. From a phenomenological point of view, the basic assumption is that any galaxy density field can be decomposed into a basis of a number of fields. Each of these fields is computed by weighting the matter density by the properties each of the mass elements had in the initial conditions. These properties are defined by the symmetries of the physical laws encoding structure formation. For example, the first element of the basis expansion is the dark matter density field itself, since we expect the galaxies to follow the dark matter distribution. The second element is also the dark matter density, but each mass has been weighted by the value of the density field it had in the initial conditions. Therefore, high-density structures, where this linear density field is larger, become more relevant. Its physical interpretation is that the places where you have collapsed dark matter structures will have a larger density of galaxies. The third element of the expansion weights the matter field with the linear density squared, making the galaxy distribution even more sensitive to these high-density peaks. We know, however, that galaxy formation also depends on different physical quantities than the density of dark matter. They depend, for example, on the tidal field and on higher order derivative terms. That's why there are two other fields as the basis elements in this expansion. One represents the tidal forces, potentiating the ability of filaments and sheets of the cosmic web to create galaxies, and the other represents a higher derivative term, the Laplacian of the linear density field, that encodes the possible dependence of galaxy formation on its curvature. We can include more terms, but we decided to stop at second order for this model, since we expect terms to be like higher order terms to be like less relevant. Note that each of these basis terms is multiplied by a free constant bias parameter that measures the response of each of the galaxy density to changes in any of these zone fields. As you can see, this is a model that works at the field level, so in principle, it could be tested and used at any higher order statistic. However, because we need an n-body simulation per cosmological parameter that we test, computing the model becomes very computationally expensive, and we only have emulators for the power spectrum currently. That's why we stick to the power spectrum in this work. To end my brief summary of the BACCOemu analysis, let me quickly skim through the validation that we made before sending the results to the collaboration. The first thing was to test that the model gives unbiased cosmological estimation on unmasked galaxy mock catalogs that we generated, okay? And we found that we were unbiased. Then we checked that the results were robust for different choices of scale cuts. So in the figure, you can see the comparison between a Kmax of 0.2, which is a common cut for perturbation theory analysis, and a Kmax of 0.5. The mean of the cosmological parameter is roughly unchanged, but the contours are tighter. So that's the meaning of robust, that the mean is not really changing. Since we are using n-body simulations and emulators, there is an intrinsic amount of noise and errors that we are including into the model. That's why we also accounted for different degrees of theoretical error budgets, finding that no relevant shift in the recovered parameters. Lastly, we checked the robustness of the inferred cosmological parameters with different amounts of information by removing multiples of the power spectrum in Redshift space. As you can see in the plot, we found consistent results when removing the hexadecapole, though there is a slight shift of the expected value of sigma 8 that will become relevant when discussing about post-unmasking results. And that's it. This is my summary of the BACCOemu emulator analysis. So cheers and thank you.
The EFT FBI team analyzes the real space mocks directly at the level of the galaxy three-dimensional field. Our data vector consists of all Fourier wave vectors that represent the 3D galaxy fields Our parameter space consists of the entire set of Fourier modes plus the sets of cosmology and galaxy bias parameters. The motivation behind field-level inference is to access only information in the data. There's no data compression, so there should be no information loss up to the scale cut of the model and the likelihood. In a recent paper, which you can find more details about by clicking on the thumbnail, we show the field-level statistics provide a very significant improvement over the standard power spectrum plus bispectrum statistics when quantified in terms of constraints on the parameter sigma 8. The model and inference framework we use is the Lagrangian EFT-based forward model of cosmological fields, aka left field, developed by the left field group. Here, the group is represented by the EFT FBI team with two members, Fabian Schmidt and myself. The left field forward model starts from Gaussian initial conditions and follows the gravitational evolution forwards with Lagrangian perturbation theory. Model prediction for the galaxy field can be constructed either in Lagrangian or Euclidean space through the EFT bias expansion, connecting the matter and galaxy fields on linear and quasi-linear scales. The small-scale physics are either suppressed or marginalized over, in which case they contribute to the stochastic field epsilon. This stochastic contribution is captured by the EFT likelihood. Left field is very fast and efficient. Even better, it is differentiable. This allows us to perform Bayesian inference using gradient space sampling method like the Hamiltonian Monte Carlo HMC. For our validation tests within this data challenge, please see the longer video. In summary, EFT FBI assumes a forward model based on Lagrangian perturbation theory and EFT bias expansion, and an EFT likelihood for the galaxy stochasticity. The EFT bias expansion, as explained by Misha, relies only on protected symmetries of gravity, namely the equivalence principles. The expansion consists of operators constructed out of the large-scale matter field and combinations thereof. The EFT likelihood is Gaussian with a diagonal covariance up to leading order. Let me now move on to model validation. Initially, we planned to participate in this challenge at the level of only inferring the cosmology plus bias parameters at fixed initial conditions. That is, we would fix the parameters describing the Fourier phases of initial conditions to the true phases in the mock simulations. Let me label this fixed IC analysis as stage 1. We use only a single realization of the real space mocks for this analysis. In the paper, I labeled that particular realization as box 1. After our stage 1 submission, the challenge organizers reviewed that our submission was within 2 sigmas of the ground truth. They further encouraged us to move forward with a full inference, inferring both cosmology plus bias parameters and the initial conditions. Let me label these 3 IC analysis as stage 2. This is the reason why we ended up with a 2-stage validation. It's important to keep in mind that stage 1 validation tests were performed on a single realization of the mock at fixed initial conditions. In general, we look at convergence of the inferred sigma 8 as a function of the scale cut Kmax for a variety of choices in modeling ingredients and analysis settings. Essentially, that was how we determined the Kmax up to which we trust our model. In the paper, you will find details about these choices, but here I'm showing sigma 8 convergence on the y-axis as a function of Kmax on the x-axis for 2 EFT bias models, the second and the third order bias expansions. For both stage 1 and stage 2 submissions, pre-unmasking, we settled with the second order bias model and a Kmax of 0.1 h megaparsec inverse, based on the results of this test. Let me next talk about inference validation, namely validation of our sampling scheme and posterior quantification. In stage 2, unlike the other teams, our team analyzes each individual 10 realizations of the real space mocks. This is because averaging the data vector over 10 realizations wouldn't make sense for field level statistics, as the mean in this case would be close to 0. That is, we would actually be washing out a signal. Having access to parameter posteriors from individual mock realizations is a good consistency check. And here on the left, I'm showing how 10 posteriors are all consistent with each other over the entire cosmology and bias parameter space. On the right, I'm further showing the autocorrelation of these parameters as a function of the raw samples in our MCMC sampling chains. Since we are extending the parameter space up to north of 800,000 dimensions, one of my questions, our ability to efficiently explore this huge dimensional space and properly estimate the posteriors or quantify the uncertainties. And here I'm showing that A, this is not really a problem of our analysis within this challenge, and B, our posterior and error bars are certainly not underestimated because of sampling issues. For further details of the EFT FBI analysis, please check out section 5.3 of the paper. In particular, our post-unmasking study is explained in the end of section 5.3 and discussed in section 6.3.
Hello, I am Enrique. I am a postdoc at the Waterloo Center for Astrophysics, and together with Carolina Cuesta Lázaro, who is a postdoc at MIT and Harvard, we carried out the density split clustering analysis for this challenge. The idea of density split is to characterize how galaxies cluster on different environments of the cosmic web. So we start off by generating random query points in the cosmological volume, and we measure the local density of galaxies around each of those points. We then proceed to split the query points into different quintals according to their local density. So for instance, from this figure, we can see how the first quintal, shown on the left, is probing low density environments in the large scale structure akin to cosmic voids, whereas the last quintal on the right is probing high density regions akin to clusters of galaxies. Once the query points have been split by density, we can then calculate clustering statistics for each of them separately. In particular, there are two statistics we focus on. The first one is the autocorrelation function of the query positions in each quintal, as exemplified on the left. And the second one on the right is the cross-correlation function between the query positions and the redshift space galaxy field. Here is how these different statistics look like in practice. Here each color is representing a different density quintal, and as you can see, we have access to most of the standard features that you would find in the standard 2-point correlation function, such as the baryon acoustic oscillation bump around 100 megaparsecs over age. But the idea is that by probing each environment separately, we gain sensitivity to non-Gaussian features of the galaxy density field, especially on small scales. And in previous work, we have shown that this can lead to substantial improvements in cosmological constraints compared to the standard 2-point clustering analysis. To apply this method to the Beyond 2PD challenge, we trained emulators based on BACCOemu simulations by adopting a halo occupation distribution model to populate the dark matter halos with more galaxies. We also used BACCOemu simulations to construct a covariance matrix, and we separated out some simulations for testing and validating our pipeline. We tried many different things to ensure that the cosmological constraints we were getting were robust. So among the things we tried, we adopted different scale cuts. We tried removing parts of the data vector, restricting some of the flexibilities of the HOD model, such as turning off the assembly bias and the velocity bias parameters. But overall, we found that the resulting cosmological constraints under all these different setups were consistent with each other to within 1 sigma or better, which gave us confidence that our analysis was ready to be submitted to the organizers of the challenge.
Hello everybody, my name is Carol Cuesta Lázaro, and I'll be introducing work done by Sandy Yuan on K-Nearest Neighbours statistics. Sandy was looking at what is the probability of finding a kth neighbor around a galaxy at any given pair separation? So in particular, you can see here on the right-hand side a two-dimensional distribution because he was splitting separations along the line of sight and perpendicular to the line of sight to be sensitive to the effect of redshift space distortions. But here what you see is the cumulative distribution function of finding a galaxy, a second neighbor, at any given pair separation. So go from 0 to 1 on large scales where you found all your second nearest neighbors. This is how it looks like when you place yourself around a galaxy. This is what here refers to as the DD k-nearest neighbor, or data, meaning the galaxies. But you could also place yourself around a random point in the survey volume. So this is called the RD k-nearest neighbor, random data. In this case, you'll be sampling the volume of the survey, which is mostly consists of voids, so you'll be more sensitive to what's happening in underdense regions, whereas the DD flavor will be more sensitive to the halo galaxy connection, or where the galaxies are doing on small scales. The shapes of these 2D distributions, like the one you see on the right-hand side, can be used to constrain cosmology, and in particular, Sandy found that it's very constraining of sigma 8. Finally, I'd like to draw your attention to the very cool paper that Sandy wrote about how we could validate our smaller scale modeling of the halo galaxy connection by fitting some statistics and predicting others. If you really found a robust way to model the halo galaxy connection, you should be able to make predictions with it. In particular, he was fitting the DD flavor of the k-nearest statistics and predicting the RD flavor. Here you can see 3 different models of the halo galaxy connection and how one of them was doing much better than the other. But if you'd like to learn more about this, I suggest you look into the paper at the archive. Thank you.
Hi, I'm Chirag Modi, and I'll discuss the simulation-based inference component of this mock data challenge. And this was work done by me and Changwoo Ha. So simulation-based inference has become increasingly popular in cosmology because it does not rely on making any assumptions on what the distribution of your data looks like. So for example, it doesn't rely whether your data is Gaussian with some known covariance or not. Instead, it tries to learn the likelihood distribution of the data directly from high-fidelity simulations using neural density estimators. An advantage of this is that we can now use any statistic in any regime that can be simulated, and we are no longer restricted to having a theoretical model for these statistics. So for this mock challenge, we used power spectrum multipoles and Bispectrum, and we used them up to the small scales of k of 0.5, where we do not have theoretical models from effective field theory or perturbation theory so far. A flip side of this, however, is that because we are using simulations, our final analysis is limited by the quality of the simulations that we use. So for this mock challenge, we used Kyoto simulations, which is the largest simulation suite we have available in cosmology for SBI. But every individual simulation in this is basically 1 gigaparsec in volume. This is much smaller than the 8 gigaparsec volume which was used for generating the mock data for this challenge. And as a result, the simulated data that we used for training our simulation-based inference procedure had much smaller signal-to-noise ratio than the mock data for analysis, especially on the large scales. And this is reflected in our results, which are shown here on the left, and our contours are much broader as compared to the other exercises because of this lower signal to noise in the training simulations that we used, especially for omega matter, which is much more sensitive on the large scales than sigma 8. Now, this is the broad overview of our simulation-based inference and our results. We'll now dive into the details of the simulation-based inference. The broad realization behind simulation-based inference is that even though we do not have the correct data likelihood distribution, or we do not have correct theoretical models for this, but the fact that we have a simulation means we can generate samples from this data likelihood distribution. And the way to see that is basically to see how we generate simulations in the first place. We begin by some model parameters, which are drawn from their own prior distribution. So this would be the cosmology parameters. We throw these into a simulator, which has its own latent parameters drawn from their own prior distribution. For example, the initial conditions of the universe. And then we run the simulations and out comes a data observable, which can be a power spectrum, bispectrum, or the full density field. Now, if you drop the dependence on these latent parameters, then this data is basically a draw from this conditional distribution, which is exactly the likelihood distribution that we care about. So generating simulations basically is equivalent to generating samples from this joint distribution of the model parameters and the observed data. To use this for inference, we then convert this into a density estimation problem. We are interested in learning the posterior distribution of the model parameters given the observed data. So we begin by assuming that this posterior can be captured by a flexible family of parametric distributions Q, and for maximum flexibility, we'll model this Q using neural networks called normalizing flows. Now we want to fit for these distribution parameters, which is the weights of these neural networks phi, such that our parametric distribution matches our target posterior. And this can be done by maximizing this conditional probability distribution of the model parameters conditioned over the data. And we do this over all the training simulations generated from this prior joint distribution. Once you have done this, once you have trained this normalizing flow, then given any new data vector, for inference, all you have to do is query this trained normalizing flow to generate samples from the corresponding posterior distribution. Now, this is a general methodology, and for this particular data challenge in cosmology, we follow this procedure more concretely. So we use the 2000 n-body simulations from this kth simulation suite, which varies these 5 cosmology parameters over a broad Latin hypercube. In every simulation, we find dark matter halos using both Friends of Friends and Rockstar halo finding technique for maximum robustness. And then each of these halo catalogs, we populate them with galaxies using halo occupation distribution model. In particular, we use a 9-parameter HOD model, which has the 5 parameters from the 2007 Zeng model, and 2 parameters for assembly bias and 2 parameters for velocity bias. For every halo catalog, we'll generate 20 independent HOD realizations by sampling these HOD parameters over a broad prior range, and during inference, we'll infer both the cosmology parameters and the HOD parameters simultaneously. Then for each of these galaxy catalogs, we evaluate the power spectrum multiples and the bispectrum multiples. This will be our data vector. And then to learn the posterior, we use masked autoregressive flows, which is a special kind of normalizing flow, to learn the posterior conditioned on this data. In particular, we train 400 different networks for, again, robustness by varying different architecture elements. This is computationally cheap. Training each network takes 3 to 5 minutes on one CPU. And after training these 400 networks, we take 10 of these which had the best validation loss and create an ensemble of this as our approximation for the posterior distribution. To check that our pipeline is accurate, we have a held-out test data set of 300 simulations on which we do this inference, and we generate coverage plots like this. If our posteriors are well calibrated, then this coverage plot should basically follow the diagonal for different parameters. I'm showing here that it does for omega matter and sigma 8, giving confidence in our pipeline. And yeah, based on this, we then take these ensemble of neural networks as our approximate posterior and apply distribution, and apply these on the mock data set provided by the mock data challenge and get constraints like this. Again, the caveat here is that because we have used simulations for training which have only 1/8 of the volume of the simulations which were used for generating the mock data set, our posteriors are much broader as compared to the other analysis. Now, this would be a problem for any of the future analysis that we would do on actual cosmological surveys. And to overcome computational bottlenecks like this, we've been working on developing new techniques like hybrid simulation-based inference, which would combine perturbation theory analysis on the large scales with simulation-based inference only on the small scales, so that we do not pay the penalty, so we're not limited by the computational bottlenecks in this case. Thank you.
Hi everyone, I'm Giovanni Verza, and I will present you voice statistics used in this challenge. This work was made in collaboration with Sofia Contarini, Nico Hamaus, and Alice Pisani. Cosmic voids are the large underdense region in the galaxy distribution, and this team focuses on constrained cosmological parameters using voice statistics. The reason of that relies in the complementarity of cosmic voids with respect to standard statistics such as the 2-point statistic of galaxies, and it has been shown in the literature that cosmic voids provide extra information. In particular, they show some orthogonality in the parameter space. For this analysis, we detect voids in the galaxy light cone, and we consider two different void statistics, the void size function and the void galaxy cross correlation function. The void size function is the number density of voids as a function of the size, and the statistics mainly depends on the matter power spectrum. It is possible to theoretically predict the size distribution of voids reaching a fixed value in their density contrast of matter, and to match this theoretical definition, we post-process our void catalog in order to have the void radius reaching a fixed density contrast in the galaxy distribution. The other statistics is the void galaxy cross correlation function that can be measured by stacking the void density profile in the galaxy distribution. From the cosmological principle, we can imply that stacked voids are spherically symmetric, and so they are statistically isotropic in real space. So they can be used as standard sphere to measure the distance ratio through geometrical distortion sourced by the Alcol-Paczynski test. And in this way, we can use the void galaxy cross correlation function to constrain the expansion history of the universe. And now I'll go more into the details of the theoretical models. For the void size function, as described before, it is possible to theoretically describe the size distribution of voids reaching a fixed value in their matter density contrast. However, in galaxy survey, we have only access to galaxy density contrast, and we therefore need a model for the bias relation between the galaxy and matter density contrasted voids. And for that, we use a parametric expression. However, we do not assume any prior on the parameter of the bias relation in this analysis, and this makes our model not sensitive to the normalization of the power spectrum, which is sigma 8. However, the shape of the void size function allows us to constrain omega matter. Concerning the void size function, as described before, from the cosmological principles follows that stacked voids are statistically isotropic in real space. And this means that we can infer the spherical average density profile directly from data without any model using the projection technique. Then we have peculiar velocities that cause voids to appear anisotropic in redshift space. And in this analysis, we assume that the velocity field in and around voids follows the linear dynamics. And as a last assumption, we assume that the relation between galaxy density contrast and matter density contrast in and around voids can be described by a linear bias relation. And both these assumptions have been widely verified in the literature. Then this model also considers two nuisance parameters that accounts for systematic effects, such as inaccuracy in the projection technique or effect in the void sample, or selection effect, or effect due to the nonlinear redshift space distortion. Then, concerning the validation for the void size function, we perform a number of tests to check the stability of the result, and in particular concerning the minimum void radius. The choice of this radius is a trade-off between maximizing the statistics and also being sure to be above the scale where void counts incompleteness is stronger, and this is due to the mean galaxy separation of galaxies that introduce a scale under which we cannot resolve the spatial distribution of voids. And so we check various minimum void radii, and we found that over a certain scale, the constraints of omega matter are always consistent within 68%. We then also verified the impact of assuming different fiducial cosmology. In particular, we consider different value of omega matter, both in our void finding algorithm and in the theoretical model, in the fiducial cosmology of the theoretical model. And we find consistent results, consistent posterior distribution within 68% of percentage in a range of plus minus 0.04 of omega matter. Then, for the void galaxy cross correlation function, It is worth noting that this analysis it is not restricted on large scales only. Linear theory accurately describes the void galaxy cross correlation function at all scale, from the inner to the outer region of void. However, both the void identification method and estimators for the void galaxy cross correlation function are affected by sparse sampling of tracer, and this results in spurious voids, and spurious voids affect our analysis. So we have to cut all the spurious voids, and for that we cut all voids smaller than a given scale, and we measure these scales as a multiple of the mean galaxy separation. In particular, we choose 5 mean particle separation as a conservative choice, but we verified that for all minimum radii larger than 3 times the mean galaxy separation, our posterior distribution converges to, let's say, a similar distribution. So that's all from the Cosmic Voids team, and if you have more questions or curiosity about Cosmic Voids analysis, please check out section 5.7 in the paper. Thank you.